actual product. So my name is Omer, and I'm an embedded systems engineer. I like tinkering a lot, and hardware is fun. So as I mentioned, we're going to talk about how to turn an idea into product today. There really isn't that much magic. That's actually quite misleading. Majority of the stuff I'm going to talk to you about today is pretty much common sense. So if you've done any hardware manufacturing before, then sorry, there might be some boring slides. Instead of dumping links on the screen, I've put them all here. So if you just head there, I've also added some notes there. In case you're typing this down or writing this down, let's do a little quick survey. Hands up if you've developed a hardware product in the past 2 years, 3 years. Oh wow. Did you use any crowdfunding services by any chance? Okay. Did you rely on any desktop manufacturing or quick prototyping, stuff that seems to be happening around? Good, cool. So it's a good time to be a maker. We have everything at our fingertips. So you want embedded Linux boards? Spy a BeagleBone or a Raspberry Pi. Do you need PCBs? There are loads of little small outlets that will produce a few PCBs for you. You want sensors? Just head to SparkFun or Adafruit and they will sell you breakouts that you can use. So this is the first element of why it's so easy to go from an idea to product these days. Dream of something or think of something in your sleep and wake up the next morning, look up some sensors, and you could start prototyping in the next couple of days after that, basically. The second element is the whole desktop manufacturing, 3D printers, which basically means you don't really have to leave your study to develop products. You could be in your boxer shorts and still design things without leaving your desk. If you don't have any of these things, well, we have very cheap manufacturing services available as well. So that monstrosity is a beautiful 3D printer that probably costs, well, quite a bit of money. But you can send your design files off to one of these manufacturers and they will send you your finished object in a couple of days after that. Or if you want something laser cut, there are loads and loads of little outlets that will cut them for you. And finally, the third element which makes manufacturing or going from an idea to product easy these days is the crowdfunding stuff. Now this used to be a huge buzzword up until very recently, but there's quite a bit of, quite a few success stories coming out of, mainly Kickstarter on the hardware front. But there's also, if you have backed any hardware projects on Kickstarter, there's no doubt you will have seen delays in shipments and stuff, because most people don't really understand how to go from 1 unit to 1 million units. It requires a different way of thinking. It requires certain things to be considered from the get-go, and we're going to try and cover some of these in the next 15 or 16 minutes, 39 seconds. So this is a very simplified, overly simplified diagram of essentially what some of these steps are when you're going from an idea to product. We're going to cover these individually, so I'm not going to go and read out everything that's on the slide, but what I wanted to say is this is not really a sequential process as it looks like on this diagram. You could be prototyping and changing specification at the same time. Ideally you shouldn't, but these things happen. Or your requirements might change, which might change your production schedule, or compliance testing might lead to design changes and so on. The key elements that you need to take into account when you're designing or when you're designing something that's going to be manufactured is DFM, Design for Manufacturability. Now, most of it boils down to common sense, as I mentioned, and it's things like keeping things simple helps. It confuses less people, and being clear about your specification helps. Not using custom parts that require threading of cables, whatever helps, because that reduces the time that's required to manufacture your stuff. And overall automation and simplification are the key points of DFM when you're manufacturing something. Now, when you're tinkering on a little hardware project of yours, you don't necessarily sit down and plan things down to the very minuscule details. You just tinker. That's in the name. So you can't really do that when you want to design something that's going to be manufactured by someone else, probably in another country or in another continent. So the first thing you should do really is to sit down and write what you're doing, what your product should do. This is boring. No one likes documentation, but coming up with a functional spec is a good start, because this helps you sort of classify your ideas into sections and basically helps you throughout the rest of the process. Another thing is, when you're, again, tinkering, you just grab stuff, available stuff from your junk page, or old components left out from another project, something like that. This doesn't go very well with manufacturing. So, stuff like dumping things on a breadboard, great for prototyping, but ideally you should be utilizing surface mount technology, which could be automated very nicely using some pretty awesome robots called pick and place machines. Now, again, when you're tinkering, you don't really select components based on manufacturability, but when you're using these sort of manufacturing techniques, you have to buy components in reels, and they come in little tapes so that they could be placed into these awesome robots so that they can be placed on the circuit boards. Bigger items need to be purchased in waffle trays. They are actually called waffle trays. Again, the same principle applies. The little head pops down and puts it on the circuit board. Now, component selection is probably the key element of designing. So packaging, what sort of package these devices come in. The smaller the package, the better it is, because you can reduce the size of your circuit boards. But size doesn't necessarily mean everything, because you might be mandated by the form factor of the thing that you're building. But surface mount packages are always better because they can be placed easily. Minimum order quantities. If you're only producing 100 of something, do you really need to buy 5,000 of something? Is that the minimum order quantity of that particular component? Or can you use services like re-reeling that many vendors do to buy a small percentage of that? Second sourcing, can you buy that component from another vendor or another manufacturer? For certain things like microcontrollers, this is not possible. You're not going to buy an ARM processor from Microchip or an Intel processor from AMD. And is the part you're using going to go obsolete anytime soon? This does require some digging around and possibly talking to people, but it's pretty crucial. You need to ensure that the part you're using is going to be available when you actually get to production. So how long will it take you to get these parts, lead times? And logistics. Most of these parts are manufactured somewhere else. You have to take into account import duties, processing delays, for cryptographic stuff, export regulations and stuff like that. And also, this is very important, you should be very careful when you're sourcing components from, random sources, basically. Random counterfeit silicon stuffed in, an Atmega case is actually a thing that exists. So once you have these components, you dump them all in what's known as a bill of materials. This is a document that contains all the items that you're using on your circuit board, the descriptors of them, descriptions, the order codes, and notes, and packages as well. And again, this is not a sequential process, by the way. Slide decks do work in a sequential manner, but these things all happen together. So, next step after you have tinkered on your little breadboard is to actually put these things in a schematic diagram and layout. I'm not going to go into this. On the little document that I shared at the first slide, there are some links. If you haven't done this before, you can follow that. A couple of things you need to be careful with printed circuit boards. Your footprints should be DFM reviewed, essentially. So solder mask clearances should be, pads should not have any solder mask on them or silk screen on them, or your pads should be long enough so that the pick and place is not a perfect sort of process, so there's a bit of leeway for moving, etc. Mirrored footprints, we've all done this before, especially with DB9 connectors and stuff. Ensure that the orientation of your connectors are correct. Spacing clearances, don't rely on the absolute maximum or minimum limits of printed circuit board manufacturers, sort of quoted specs. They lie sometimes. And when you're manufacturing a circuit board, you have to panelize things. I have a picture of this in a minute. And fiducials is, they cover the whole process of how to go from one board to a full panel. So you can separate your boards two ways. One of them is called tab routing, and the other one is called V-scoring. V-scoring is when boards are, right next to each other and just snap them off. And tab routing is a little more complex. You have tabs holding boards together, and they're routed from a channel. And those tiny things that hold the boards attached to the tab is called mouse bytes. When you're panelizing, you could employ some testability tactics, like in this instance, again from the EV blog. It's an awesome tutorial on DFM on panels. You can see some traces going to the outer edge of the panel, where you can power all the boards directly from an outside source. Or if your processors are J-type capable, you can have a J-type chain, and you can test stuff very easily while your circuit boards or PCBs are still attached to the panel. Now, as I said, PCB manufacturing is a very complex process, sometimes especially when you're doing multi-layer stuff. This is many layers, this is not 4 layers, but there's I think it's a 30-minute video about this process available at that link. I suggest you watch this if you want to get PCBs manufactured, because it kind of helps you understand what's going on, and it kind of shows the pain points and where you should pay attention to and stuff. One thing that's crucial is never ever trust the output of your PCB CAD software. Use a Gerber Editor or Gerber Weaver to actually look at your files. Gerbers are essentially the files you send off to your manufacturer. They're the manufacturing data. So ensure that your Gerbers look sane before you send them off. And also, some PCB tools now support 3D modeling of components. This, of course, relies on the fact that you should have correct 3D models. But if you do, it helps you spot certain things like, does anyone see the problem on the circuit board? Yeah, so when you're manufacturing, when you're prototyping at home, this is perfectly fine. You'll just chop off the side of one of these connectors, but you can't really chop off 1,000 or a million connectors. That's just too much time. So once you have your circuit board stuff, details, schematic, and Gerbers, you put together a little README file with your notes on it. So it could be simple things like board outline is on top, silk screen, just basic notes about your manufacturing process. Now, we've talked about electronics so far, but quite often there's a mechanical side to the whole story as well. So I know nothing about 3D modeling, so I've asked someone else to do this for me. But basically, this is a parallel process happening. You should sort of be in touch with whoever is designing the case, because your circuit board should ideally fit into this enclosure that it's designed for. So at this point, you have a lot of documents. So you have spec documents, bill of materials. It's getting quite complex at this stage. You have to manage documents, different versions, different permutations. Use version control. Version control isn't that scary. GitHub is a good source. I'm really running out of time. So what GitHub or Git or any version control system really allows you to do is have commits and sort of group them in tags or releases. So this helps you create, say, version 1 of your board with all these commits, whatever. These are not hardware-related commits, but kind of gets the point across, I guess. So once you package your design data, you send it off to a manufacturer. We're still talking prototype actually at the moment. So you want a prototype board, you just generate Gerbers, design documents, send them off, wait for some time, and then you receive your first prototypes, or revision 0. Now, no one gets things perfect in revision 0. A couple of revisions before production is actually the norm, the standard. Once you get revision 0, you start prototyping. And this is where you actually realize your clever power design didn't really work, and there's quite a bit of noise. I guess not too much. But still, you have to ensure what you have designed is what you wanted in the first place. So you should compare the outcome or the physical results that you get with the spec document that you have prepared. This is why the spec document is important. And again, in parallel, the mechanical stuff starts arriving, and you should start testing the fit. Does it really fit? Do I have to chop off a couple of millimeters on the circuit board? So, as I said, this is not, you're not going to get everything right in revision 0. So, you repeat this process until you get things right. And once you're ready, again, let's have a look at this diagram. We're currently at somewhere around here. So, once you're ready to send your files off to the CEM, the contract electronics manufacturer, you can choose CEMs from very small scale ones to very large scale ones, local ones to global ones. It entirely depends on your budget, how fluent you're in Chinese, and also what are you producing? Are you producing something that doesn't require special manufacturing techniques only available at one CEM, or just something generic that anyone can produce? Anyway, the point is, I'm not going to tell you which CEM to use because it's highly application dependent, but you should shop around. There are, the scale that they operate at and the costs and the treatment you'll get are very different between CEMs. So they will probably reply with something along the lines of this. Well, we'll charge you X pounds or X dollars each. We'll deliver, X weeks from placement of order. Here's the important part. Assembly and all manual steps will be charged something like per minute. So this is why it's important to try and automate as much as possible and reduce the manufacturing time, because it's actually real cost. And also you will have to pay one-off charges for tooling and all sorts of other NRE expenses. So one step in reducing the manufacturing time is actually automating your testing. So you have a circuit board. If it requires someone manually plugging things in, putting some probes on it to look at an oscilloscope output, whatever, then you've lost it. You have to automate that and essentially turn that into, plop it onto a test jig. If it beeps, it's okay. If it doesn't beep, just throw it in the bin to be looked at afterwards. Now there's a very good example of this, again, from the EEV blog, about actually developing these custom little test devices to automate the testing procedure. And you can see that there's a little edge connector here and this box over there that is used to power the boards directly without having to put batteries in each individual one and so on. So again, automation is the key, and things like the little circuit boards to help with testing are actually quite a good idea. Now, I'm not going to spend much time talking about regulations or compliance testing, etc., but again, depending on your application and depending on the markets that you're selling to, these might be necessary. I absolutely love this. It's Ed the handyman chained to symbols to ensure that he cannot design dangerous products. So the regulations and certifications are there to actually protect people. I mean, if it's a medical device, you would have to go through some pretty stringent testing. And really, you should probably employ someone who knows what they're doing for this. This is quite a complex process. So if everything goes well, you will go from your breadboard prototype to an actual product. And it's actually one of the most satisfying feelings, seeing your idea turning into a tangible object that's used by other people and stuff. So with that said, thank you very much.